And we're back. We're going to continue looking at graphs of important functions for grade 12 advanced functions course. The next one we're going to study is the square root of x. So this is a square root function. And we want to see what the shape is. So let's make a small table of values. For this function, we want to recall that we cannot take the square root of a negative number. And I'll leave that for you to research why. That could be another lesson. If you have questions, you can see me in class. So let's choose values for x that are positive. So we're going to choose 0. We're also going to choose 1, 4, 9. We could also choose 16, 25 if we like, but those are getting kind of big for our grid. The reason we chose these numbers is because those are perfect squares. When we take the square root of a number, we want to get a good graph, we want to choose numbers that are perfect squares because those will give us whole number values when we take their square root. So when we're substituting these values in, the square root of x, square root of 0 is 0, square root of 1 is 1, square root of 4 is not 4, it is 2, because 2 times 2 is 4. Square root of 9 is 3, square root of 16 is 4, square root of 25 is 5. So when we plot these values, looking over at our graph, 0, 0, 1, 1, now we go over to 4 and up to 2, over to 9 and up to 3. You can see we don't have room to plot the 16 and the 25. And we're not going to plot any values that are negative because those fall outside of the domain of this function. We cannot take the square root of a negative number. So now we connect these in a smooth curve. Next we will look at the function f of x equals 1 divided by x. This is known as a reciprocal function. We are taking 1 and dividing it by our value of x, which is our variable. So let's make again a small table of values. And for this one we can take negative numbers and positive because we are allowed to divide by a negative number. That's perfectly fine. So let's pick some values that are similar to what we would use if we were graphing a quadratic function. We'll do negative 3, negative 2, negative 1, 0, 1, 2, 3 as our sample values. If we needed to go higher, we could. Now, when we substitute these in, f at negative 3 is going to be 1 divided by negative 3, which is negative 1/3, or if you prefer, negative 0.3 repeated. 1 divided by negative 2 is negative 1/2, or if you prefer a decimal, negative 0.5. 1 divided by negative 1 is negative 1. Now what's 1 divided by 0? Well, that's undefined because the cardinal rule of math is we are not allowed to divide by 0. 1 divided by 1 is 1. 1 divided by 2 is 0.5. 1 divided by 3 is 0.3 repeated. Now this is not giving us a very clear picture. Let's see what we get when we plot this. Negative 3, negative 0.3. Negative 2 is negative 0.5. Negative 1, negative 1. 0, undefined, so we don't put anything there. 1, 1. 2, 0.5, and 3 is 0.3. Doesn't give us a very good picture of what's really happening. We can see that the points are getting closer to the x-axis as x gets further out, and here getting closer to the x-axis as it gets further out. But what I really want to know is what's happening in here, in between negative 1 and 1, or between 0 and 1, 0 and negative 1. So let's do a few more values here in our table, I'm going to choose negative 0.5 for x, negative 0.25. And I'm going to choose 0.25 and 0.5, just to get a little bit more idea of what is going on. So if I substitute negative 0.5 into x, I get 1 divided by negative 0.5. And if you're not sure how to do that on your calculator, so 1 divided by negative 0.5 is negative 2. 1 divided by negative 0.25 is negative 4. 1 divided by 0.25 is 4. 1 divided by 0.5 is 2. So that takes care of the values between 0 and 1 and between negative 1 and 0. So what do those look like? So at negative 0.5, the result is negative 2. At negative 0.25, which is even closer to the y-axis, the result is negative 4. So we can see that this curve is heading downward, approaching the y-axis, but it's never actually going to touch it. And we get a feature here called an asymptote, where we see the graph approaches this line but never quite reaches it. We have the same thing on the other side. At 0.5 it was 2. At 0.25 it was 4. We can see another asymptote feature here. So we actually have two asymptotes, one along the y-axis, there's a vertical asymptote, and one along the x-axis is a horizontal asymptote. Okay, and the last function that we see on this sheet is called the absolute value of x. That's when we have these two lines around the x. So that's called the absolute value function. We're going to be discussing the absolute value function a little bit more in class, but just to give you a general understanding, the absolute value function tells us the distance that x is away from the y-axis. So if, for example, I take the absolute value of negative 3 is here, and it is 1, 2, 3 units away from the y-axis. So absolute value of negative 3 is just 3. Absolute value of 3 would also be 3, because here's 3. It's also 3 units away from the y-axis. So absolute value just tells us the distance that that number is from the y-axis. So if the number is negative, it just essentially takes that negative sign off. Not a difficult thing. So we'll just do a quick little table of values. And we'll just pick a few negative and a few positive. This is all we need. Negative 2, negative 1, 0, 1, 2. So we already know the negative 3 and 3, which is why I didn't include them. So absolute value of negative 2 would be 2. Absolute value of negative 1 is 1. Absolute value of 0, well, it's right here. It's on the y-axis, so it's just 0. Absolute value of 1 is 1, and of 2 is 2. So we end up negative 3, 3, negative 2, 2, etc. Plotting these points. Look at that nice shape. The points line up in a straight line. So we need our ruler to connect those together. Nice, tidy function. And there is the absolute value of x.